Hello there. Tonight, we're going to explore something you experience every single day, but probably never fully understood. Something so familiar that you check it on your phone each morning, yet so mysterious that even the most advanced supercomputers in the world can only predict it a few days ahead. We're talking about weather, not just what weather is, but how it actually works. Why does the wind blow? What makes clouds form and then disappear? Why does it rain in one place and stay sunny just a few miles away? And why, on some days, does the sky seem to come alive with storms that shake the ground beneath your feet? These aren't simple questions, but the answers are more fascinating than you might imagine. Over the next few hours, we'll unravel the science behind every weather phenomenon you've ever witnessed. From the gentlest breeze to the most violent tornado, from morning dew to massive hurricanes, it all follows the same basic rules of physics. And here's the beautiful part. Once you understand these rules, you'll never look at the sky the same way again. So if you're someone who loves understanding how the world works, if you're curious about the forces that shape every moment of every day, then you're in the right place. Consider subscribing so other curious minds can find their way here too. And let's begin this journey together into the invisible ocean above our heads. Let's start with the most fundamental question. What exactly is weather? When you step outside and feel the sun on your face, or the rain on your skin, or the wind in your hair, you're experiencing weather. But weather isn't just what's happening right now. It's the entire state of the atmosphere at any given moment, in any given place. The atmosphere is that layer of gases surrounding our planet, and weather is simply what happens when this ocean of air is in motion. Think of the atmosphere as a massive, invisible sea that we all live at the bottom of. Just like the ocean has currents and waves and tides, the atmosphere has its own movements and patterns. And just like the ocean, the atmosphere is never perfectly still. It's always moving, always changing, always redistributing energy and moisture around the planet. This constant motion creates everything we call weather. Now, to understand why the atmosphere moves at all, we need to start with something even more basic: energy from the sun. Every single weather event on Earth, from a light drizzle to a Category 5 hurricane, gets its energy from the sun. The sun doesn't heat the Earth evenly. This might seem obvious when you think about it, because places near the equator are hot while places near the poles are cold. But the implications of this simple fact are enormous. The uneven heating of Earth's surface is the engine that drives all weather. Imagine the Earth spinning in space as the sun shines on it. The equator, which is the middle band around the Earth, receives sunlight almost directly overhead all year round. This concentrated sunlight delivers a tremendous amount of energy. Meanwhile, near the North and South poles, sunlight arrives at a much lower angle, spreading the same amount of energy over a much larger area. It's like the difference between shining a flashlight straight down on a table versus shining it at a steep angle. When the light hits straight on, you get a bright, concentrated spot. When it hits at an angle, the same light spreads out and becomes dimmer. This is why the poles are cold and the equator is hot. But Earth doesn't just sit still while the sun heats different parts of it differently. Earth rotates, completing one full spin every 24 hours. This rotation adds another layer of complexity to how heat spreads around the planet. And Earth doesn't just rotate, it also orbits the sun. And it does so while tilted on its axis. This tilt is why we have seasons. During part of the year, the northern hemisphere tilts toward the sun and experiences summer, while the southern hemisphere tilts away and experiences winter. 6 months later, the situation reverses. But regardless of the season, the basic pattern holds. The equator gets more direct sunlight and more heat, while the poles get less. This creates a temperature difference, and temperature differences are what make air move. Let's talk about air itself for a moment. Air seems like nothing, like empty space, but it's actually a mixture of gases, mostly nitrogen and oxygen, with small amounts of other gases like carbon dioxide and argon, plus water vapor. Air has mass, which means it has weight, and that weight creates pressure. Air pressure is simply the weight of all the air above you pressing down. At sea level, you have the entire atmosphere stacked above your head, and that creates a pressure of about 14.7 pounds per square inch. You don't feel this crushing weight because the air inside your body pushes out with the same pressure, creating a balance. But this pressure isn't the same everywhere. When air is heated, it expands and becomes less dense. When it cools, it contracts and becomes more dense. Denser air weighs more and creates higher pressure. Less dense air weighs less and creates lower pressure. This might sound technical, but it's actually very simple. Hot air rises because it's lighter, and cold air sinks because it's heavier. This single principle is the foundation of almost all weather. Let's imagine what happens on a sunny day. The sun's rays hit the ground and warm it up. The ground then heats the air directly above it. This warm air expands and becomes less dense than the cooler air around it. Being lighter, it rises. As it rises, cooler air flows in from the sides to take its place. This movement of air is wind. That's all wind is, air moving from one place to another. But why does it move? It moves because of pressure differences. Air naturally flows from areas of high pressure to areas of low pressure, trying to equalize the imbalance. It's like water flowing downhill. Water doesn't need to be pushed. It flows on its own because of gravity, always seeking the lowest point. Similarly, air doesn't need to be pushed. It flows on its own from high pressure to low pressure, trying to balance things out. Now, let's think about what happens to that warm air that rises. As it goes higher and higher into the atmosphere, something interesting happens. It cools down. You might have noticed this if you've ever climbed a mountain or flown in an airplane. The higher you go, the colder it gets, even though you're getting closer to the sun. This seems backwards at first, but it makes sense when you understand what's happening. The sun doesn't actually heat the air directly very much. Instead, the sun heats the ground, and the ground heats the air. So the air at ground level is warmest because it's in contact with the warm surface. As you go higher, you get farther from that heat source. Also, as air rises, it expands because there's less pressure pushing on it from above. When air expands, it cools down. This is a fundamental principle of physics. You can feel this yourself if you've ever used a compressed air canister. When you release the pressure and let the air expand rapidly, the canister gets cold. The same thing happens in the atmosphere. Rising air expands and cools. This cooling of rising air is incredibly important for weather because of what it does to water vapor. Water vapor is simply water in its gas form, invisible and mixed into the air. Air can hold water vapor, but there's a limit to how much it can hold, and that limit depends on temperature. Warm air can hold more water vapor than cold air. This is why your bathroom mirror fogs up when you take a hot shower. The warm, moist air hits the cool mirror surface, cools down, and suddenly can't hold as much moisture, so the excess water condenses into tiny droplets on the mirror. The same principle works in the atmosphere. When warm, moist air rises and cools, it eventually reaches a temperature where it can't hold all its moisture anymore. At this point, the water vapor condenses into tiny liquid droplets. Billions and billions of these tiny droplets together form what we see as a cloud. A cloud is literally just a visible collection of water droplets or ice crystals suspended in the air. So now we can start to see how a simple sunny day creates clouds. The sun heats the ground heats the air, the warm air rises, carrying moisture with it. As it rises, it cools. When it cools enough, the moisture condenses into water droplets, forming a cloud. This is why on sunny days you often see puffy white clouds that seem to just appear in the sky. They're forming at the exact altitude where the rising air has cooled enough for condensation to occur. These puffy clouds are called cumulus clouds, from the Latin word for heap or pile. They look like cotton balls floating in the sky, and they're one of the most common types of clouds you'll see. They form during the day when the sun is heating the ground and disappear at night when the heating stops and the air stops rising. But not all air rises straight up like this. Remember, we said air flows from high pressure to low pressure. On a global scale, this creates massive circulation patterns. At the equator, where the sun's heating is most intense, air is constantly being warmed and rising. This creates a zone of low pressure around the equator. The rising air can't keep going up forever. Eventually, high in the atmosphere, it has to go somewhere. It spreads out toward the north and south, away from the equator. As it moves away from the equator at high altitude, it gradually cools and sinks back down. This happens around 30 degrees north and south latitude, creating zones of high pressure. This sinking air is why many of the world's deserts are located around 30 degrees latitude. Deserts like the Sahara in Africa, the deserts of the Middle East, the deserts of the southwestern United States, and the deserts of Australia all sit in these zones where air is sinking. Sinking air warms up and becomes drier, suppressing cloud formation and rain, which is perfect for creating deserts. Meanwhile, back at the surface, the air that sank down at 30 degrees latitude has to flow somewhere. Some of it flows back toward the equator along the surface, completing a circulation loop. This return flow creates the trade winds, which are steady winds that blow from east to west in the tropics. Sailors discovered these winds centuries ago and used them to cross oceans. The trade winds are called that because they were so reliable for trade routes. Some of the air at 30 degrees also flows toward the poles. This air eventually meets cold air coming from the polar regions, and where these different air masses meet, you get the weather systems that dominate the middle latitudes, the zones between about 30 and 60 degrees where most of the world's population lives. This is where weather gets interesting and complicated, with constantly changing conditions, passing storms, and dramatic shifts from warm to cold and back again. But we're getting ahead of ourselves. Before we dive into complex weather systems, we need to understand one more crucial factor: Earth's rotation. Earth spins, and this spinning affects how air moves in ways that might not be immediately obvious. Imagine you're standing at the North Pole, and you throw a ball to someone standing far away toward the equator. You throw the ball in a straight line, but from your friend's perspective, the ball seems to curve to the right. This isn't because the ball curved, it's because while the ball was in the air, Earth rotated beneath it. Your friend moved along with Earth's rotation, but the ball kept going in the direction you threw it. This apparent deflection of moving objects on a rotating planet is called the Coriolis effect, named after the French scientist who described it mathematically. The Coriolis effect influences everything that moves across large distances on Earth, including air and water. In the northern hemisphere, moving air deflects to the right. In the southern hemisphere, it deflects to the left. This deflection has a huge impact on wind patterns. Remember how we said air flows from high pressure to low pressure? Because of the Coriolis effect, it doesn't flow in a straight line. Instead, it curves. In the northern hemisphere, air flowing toward a low-pressure area curves to the right, and this causes it to spiral in a counterclockwise direction around the low-pressure center. Air flowing away from a high-pressure area also curves to the right, causing it to spiral out in a clockwise direction. In the southern hemisphere, everything is reversed because the deflection is to the left instead of to the right. This is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's not random, it's a direct consequence of Earth's rotation. The Coriolis effect also explains why we have jet streams. Jet streams are narrow bands of very fast-moving air high up in the atmosphere, typically around 30,000 to 40,000 feet above the surface. They flow from west to east and can reach speeds of over 200 miles per hour. Jet streams form at the boundaries between warm and cold air masses, and their position and strength vary with the seasons. In winter, when the temperature difference between the equator and the poles is greatest, the jet stream is stronger and shifts farther south. In summer, it weakens and shifts north. Weather systems tend to follow the jet stream, which is why meteorologists pay close attention to its position. A storm forming in the Pacific Ocean will likely track along the jet stream as it crosses North America. The jet stream acts like a river of air, guiding weather systems along its path. Now let's bring all these concepts together and see how they create the weather you experience on any given day. Imagine you wake up in the morning and check the weather forecast. It says there's a low-pressure system moving into your area, bringing clouds and rain. What does this actually mean? It means that somewhere nearby, air is rising. Remember, rising air creates low pressure at the surface because there's less air pressing down. As this air rises, it cools and its moisture condenses, forming clouds. If the air is moist enough and the rising motion is strong enough, those clouds will grow thicker and taller until they eventually produce rain. The rain happens when the tiny cloud droplets collide and merge with each other, growing larger and larger until they're too heavy to stay suspended in the air. Then they fall as raindrops. But why is the air rising in the first place? There are several reasons this might happen. One possibility is that there's a front moving through. A front is simply the boundary between two different air masses, one warm and one cold. When a warm air mass and a cold air mass meet, they don't mix easily because they have different densities. The warm air is lighter and the cold air is heavier, so the warm air rides up over the cold air. This lifting of warm air over cold air forces the warm air to rise, cool, and form clouds. If there's enough moisture and the lifting is strong enough, you get rain or even storms. There are different types of fronts depending on which air mass is advancing. A cold front occurs when cold air is pushing into a region of warm air, forcing the warm air to rise rapidly. Cold fronts often bring brief but intense weather, with towering clouds, heavy rain, and sometimes thunderstorms. A warm front occurs when warm air is advancing and sliding up over retreating cold air. Warm fronts tend to bring more gradual, widespread cloud cover and lighter, longer-lasting rain. Another reason air might rise is simply because of daytime heating, like we discussed earlier with cumulus clouds. But sometimes this daytime heating can trigger much more dramatic weather. On a hot, humid summer afternoon, the sun heats the ground intensely. The air near the surface becomes very warm and holds a lot of moisture. This air wants to rise, but sometimes there's a layer of warmer air above it that acts like a lid, preventing the surface air from rising. Meteorologists call this a capping inversion. As the day goes on, the surface air gets hotter and hotter, building up more and more energy, while the cap holds it down. Eventually, if something breaks through that cap, perhaps a front moving through, or just the sheer intensity of the heating, the pent-up air suddenly surges upward explosively. This can create towering thunderstorm clouds that shoot up to 40,000 feet or higher in just a matter of minutes. These are the storms that produce heavy rain, lightning, hail, and sometimes tornadoes. They're nature's way of releasing the energy that built up during the day. Lightning, by the way, is one of the most spectacular weather phenomena, and it's a direct result of what's happening inside a thunderstorm cloud. Inside these towering clouds, there are powerful updrafts and downdrafts, currents of air rushing up and down at speeds that can exceed 100 miles per hour. Water droplets and ice crystals are carried up and down within these currents, colliding with each other constantly. These collisions cause a separation of electrical charge. Lighter, positively charged ice crystals are carried to the top of the cloud by the updrafts, while heavier, negatively charged particles accumulate in the lower parts of the cloud. This separation of charge creates an enormous electrical field, with the top of the cloud becoming positively charged and the bottom becoming negatively charged. The ground below the cloud also becomes positively charged by induction. When the electrical field becomes strong enough, it overcomes the air's natural resistance to conducting electricity, and a current flows. This is lightning. The lightning flash heats the air around it to temperatures hotter than the surface of the sun, around 50,000 degrees Fahrenheit. This sudden heating causes the air to expand explosively, creating a shock wave that we hear as thunder. Light travels much faster than sound, which is why you see the lightning before you hear the thunder. You can actually estimate how far away a lightning strike is by counting the seconds between the flash and the thunder and dividing by 5. This gives you the distance in miles. Thunderstorms can also produce hail, which might seem strange if you think about it. Hail is ice falling from the sky, but it falls during warm weather, often in the middle of summer. How does ice form when it's hot outside? The answer lies in the height of the thunderstorm clouds. Even on the hottest day at the surface, the temperature high up in the atmosphere is well below freezing. Inside a powerful thunderstorm, water droplets are carried up into these freezing levels by the strong updrafts. When they freeze, they become small ice particles, but the updrafts are so strong that these ice particles don't fall right away. Instead, they get carried back up again and again, each time picking up another layer of ice as more water freezes onto them. A hailstone is built up in layers, like an onion, with each layer representing another trip through the cloud. You can see these layers if you cut a hailstone in half. Eventually, the hailstone becomes so heavy that even the powerful updraft can't keep it aloft anymore, and it falls to the ground. Large hail requires very strong thunderstorms. A hailstone the size of a golf ball or larger indicates updrafts of at least 60 to 80 miles per hour. The largest hailstones ever recorded have been the size of grapefruits and have fallen at speeds exceeding 100 miles per hour, causing tremendous damage to anything they hit. But let's step back from extreme weather for a moment and think about more ordinary conditions. What creates the weather on a calm, pleasant day? On such a day, you likely have high pressure overhead. High pressure means air is sinking, and sinking air warms up and dries out, suppressing cloud formation. This is why high-pressure systems are generally associated with clear skies and calm weather. The air is stable, there's no rising motion to create clouds or precipitation. Often, these high-pressure systems are large and slow-moving, which is why you can have several days in a row of beautiful weather when a strong high is parked over your area. Conversely, low-pressure systems bring clouds and unsettled weather because of the rising air we discussed. Weather forecasters track these high and low pressure systems as they move across the map, and by understanding how they interact and how they're steered by the jet stream, forecasters can predict what the weather will be like in the coming days. Wind speed is also related to pressure. The greater the difference in pressure between two areas, the faster the air will flow from high to low, trying to equalize the pressure. This is why some days are windy and others are calm. On a day when there's a big difference between a nearby high and a nearby low, the pressure gradient is steep and the wind blows hard. On a day when pressure systems are far apart or weak, the gradient is gentle and the wind is light or non-existent. You can actually see this on a weather map. Weather maps use lines called isobars to connect points of equal pressure. Where the isobars are close together, the pressure is changing rapidly over a short distance, indicating strong winds. Where the isobars are far apart, pressure is changing gradually, indicating light winds. Let's talk about humidity, which is another important aspect of weather. Humidity is simply a measure of how much water vapor is in the air. There are different ways to express humidity, but the most common one you hear in weather forecasts is relative humidity. Relative humidity is the amount of water vapor in the air compared to the maximum amount the air could hold at that temperature, expressed as a percentage. If the relative humidity is 100%, the air is holding as much water vapor as it possibly can at that temperature. It's saturated. If relative humidity is 50%, the air is holding half of what it could hold. Now here's the important part. Warm air can hold much more water vapor than cold air. So the same amount of water vapor in the air will give you a low relative humidity on a hot day and a high relative humidity on a cold day. This is why mornings often feel more humid than afternoons, even if the actual amount of water vapor hasn't changed. In the cooler morning air, the relative humidity is higher. As the day warms up, the air's capacity to hold moisture increases, so the relative humidity drops even though the actual moisture content is the same. When relative humidity reaches 100%, the air is saturated, and any additional moisture will condense out. This is how dew forms. On a clear, calm night, the ground radiates heat away into space and cools down. The air in contact with the cool ground also cools. If it cools enough that its temperature drops to the dew point, the temperature at which the air becomes saturated, moisture will condense out of the air and form tiny droplets on surfaces like grass, cars, and spider webs. That's dew. It's not falling from the sky, it's forming right there on the surface because the air in contact with the surface has cooled to its saturation point. Frost forms the same way, except that instead of condensing into liquid water, the moisture deposits directly as ice crystals when the surface temperature is below freezing. Fog is closely related to dew. Fog is basically a cloud that forms at ground level. It happens when the air near the surface cools to its dew point and moisture condenses into tiny water droplets suspended in the air. There are different types of fog depending on how the cooling occurs. Radiation fog forms on clear, calm nights when the ground cools by radiating heat away. The air in contact with the ground cools, and if it has enough moisture, fog forms. This type of fog is common in valleys, where cool air drains down from surrounding hills and accumulates. Advection fog forms when warm, moist air moves over a cooler surface, like when warm air from over the ocean blows over cold coastal waters. The air is cooled from below, and fog forms. This is the type of fog that often blankets San Francisco. Upslope fog forms when moist air is forced to rise up a mountain slope, cooling as it rises until it reaches its dew point. And evaporation fog, sometimes called steam fog, forms when cold air moves over warm water. The water evaporates into the air, and because the air is cold and quickly becomes saturated, the water vapor immediately condenses into fog. You see this on cold mornings over lakes or rivers, where the water is warmer than the air and the lake seems to be steaming. Temperature itself deserves more attention, because it's one of the most fundamental aspects of weather and something everyone pays attention to. Temperature is simply a measure of how much heat energy the air has. But what you feel as temperature is influenced by more than just the air temperature. Wind and humidity both play a role in how hot or cold it feels. On a hot day, your body cools itself by sweating. The sweat evaporates from your skin, and evaporation requires energy, which is taken from your body in the form of heat. This cools you down. But evaporation happens more slowly when the air is already humid, because the air is already holding a lot of moisture. This is why a humid day at 90 degrees feels much hotter and more oppressive than a dry day at 90 degrees. On the dry day, your sweat evaporates efficiently and cools you. On the humid day, your sweat doesn't evaporate as well, and you feel hotter. This is why weather reports often include a heat index, which combines temperature and humidity to tell you what the temperature actually feels like. Wind also affects how temperature feels. On a cold day, wind strips away the thin layer of warm air that your body creates around itself, exposing your skin to the cold air and making you feel colder. This is the wind chill effect. A calm day at 20 degrees might feel tolerable, but add a 20-mile-per-hour wind, and the wind chill can make it feel like it's near zero. Wind doesn't actually change the temperature. A thermometer will read the same whether it's windy or calm, but it changes how quickly you lose heat, and that affects how cold you feel. On a hot day, wind can actually make you feel cooler by helping sweat evaporate faster, which is why a breeze feels refreshing on a hot summer afternoon. Now let's think about the daily cycle of temperature. During the day, the sun heats the ground, and the ground heats the air, so temperature rises. Temperature typically reaches its maximum in the mid to late afternoon, a few hours after the sun is highest in the sky. Why the delay? Because even though the sun is highest at noon, the ground continues to absorb more heat than it radiates away until mid-afternoon, so temperature keeps rising. After the sun sets, the ground starts losing heat faster than it gains it, so temperature drops. The lowest temperature usually occurs right around sunrise, just before the sun starts heating things up again. This daily temperature cycle is very regular on clear, calm days. Clouds can modify it because clouds reflect sunlight during the day, keeping temperatures cooler, and they trap heat at night, keeping temperatures warmer. So cloudy days tend to have a smaller range between the high and low temperature than clear days. Seasons, of course, create a much larger temperature cycle. In the summer, when your hemisphere is tilted toward the sun, days are long and the sun is high in the sky, delivering a lot of energy. In winter, days are short and the sun is low in the sky, delivering less energy. This is why summer is warm and winter is cold. The tilt of Earth's axis is what creates seasons. If Earth weren't tilted, every place on the planet would have the same length of day and night year-round, and there would be no seasons. The equator would still be hot, and the poles would still be cold because of the angle of sunlight, but there wouldn't be the warm-cold cycle that we call seasons. The tilt is about 23.5 degrees, and it stays pointed in the same direction in space as Earth orbits the sun, which means that for part of the year the northern hemisphere tilts toward the sun, and for part of the year it tilts away. Let's think about what happens at different times of year. At the summer solstice, around June 21st, the northern hemisphere is tilted maximally toward the sun. The sun appears highest in the sky at noon, and day length is at its maximum. North of the Arctic Circle, the sun doesn't set at all. It's daylight for 24 hours. Meanwhile, in the southern hemisphere, it's winter. The sun appears low in the sky, days are short, and south of the Antarctic Circle, it's dark for 24 hours. 6 months later, at the winter solstice around December 21st, the situation reverses. The northern hemisphere tilts away from the sun, days are short, and the sun is low in the sky. The southern hemisphere tilts toward the sun and experiences summer. In between, at the spring and fall equinoxes, the tilt is sideways to the sun, neither toward nor away, and day and night are approximately equal length everywhere on Earth. Equinox literally means equal night. These seasonal changes in sunlight drive changes in weather patterns. In summer, the sun's intense heating creates strong temperature contrasts and active weather, with thunderstorms and heavy rain in many places. In winter, the weaker sun and shorter days mean less heating, and weather is often dominated by large-scale systems moving across continents, bringing cold snaps, snowstorms, and extended periods of clouds. The middle latitudes, between about 30 and 60 degrees, experience the most dramatic seasonal changes. Near the equator, seasons are less pronounced because the sun is always high in the sky. Instead of winter and summer, tropical regions often have wet and dry seasons, driven by shifts in wind patterns and the migration of the zone where air rises and produces rain. Speaking of tropical regions, let's talk about one of the most dramatic weather phenomena that develops there, the tropical cyclone, also known as a hurricane in the Atlantic and Eastern Pacific, a typhoon in the Western Pacific, and a cyclone in the Indian Ocean. These are all the same type of storm, just with different names depending on where they occur. A tropical cyclone is a massive rotating storm system with winds that can exceed 150 miles per hour and a central area of very low pressure called the eye. These storms form over warm ocean water, typically when the sea surface temperature is at least 80 degrees Fahrenheit. Warm water is essential because the storm's energy comes from the evaporation of ocean water and the release of heat when that water vapor condenses into clouds. In the warm tropics, when conditions are right, a cluster of thunderstorms can organize into a rotating system. The rotation starts because of the Coriolis effect. As air flows toward the low pressure at the center of the storm system, it deflects to the right in the northern hemisphere, causing the whole system to spin counterclockwise. As more and more warm, moist air spirals into the storm, more and more water vapor condenses, releasing latent heat. This heat warms the air, making it rise even faster, lowering the pressure at the center even more, which draws in more air, which brings more moisture, which releases more heat. It's a self-reinforcing feedback loop. The storm intensifies rapidly as long as it stays over warm water and doesn't encounter hostile conditions like wind shear. which is a change in wind speed or direction with height that can tear a storm apart. At the center of a mature hurricane is the eye, a region of calm winds and often clear skies. The eye forms because the strongest winds are in the eye wall, the ring of thunderstorms immediately surrounding the eye. The eye wall has the most intense rainfall and the strongest winds in the entire storm. Air inside the eye wall is rising so rapidly that it creates a partial vacuum at the center. Air from high in the atmosphere sinks down into this vacuum, creating the eye. This sinking air warms up and dries out, which is why the eye can be calm and even sunny, while just a few miles away in the eye wall the storm is raging at its most violent. People who have experienced the eye passing over them describe an eerie calm, with the wind suddenly dropping to nothing and the sky clearing, only to have the other side of the eye wall hit with full fury as the eye passes. Hurricanes are enormous, often several hundred miles in diameter, and they can last for days or even weeks as they travel across the ocean. They're steered by the prevailing winds and tend to move westward in the tropics, guided by the trade winds, and then curve northward in the Atlantic, guided by the jet stream. When a hurricane makes landfall hitting a coastline, it brings multiple hazards. The wind itself can cause catastrophic damage, tearing roofs off buildings, uprooting trees, and turning debris into dangerous projectiles. But often the most destructive part of a hurricane is the storm surge, a rise in sea level caused by the storm. The low pressure at the center of the hurricane causes the ocean surface to bulge upward, and the strong winds pile water up against the coast. This surge can raise water levels by 15 feet or more, flooding coastal areas and causing tremendous destruction. Heavy rainfall is another major threat. A single hurricane can drop more than a foot of rain, causing severe flooding far inland, even hundreds of miles from where the storm made landfall. Once a hurricane moves over land, it begins to weaken because it's cut off from its energy source, the warm ocean water. The storm's winds decrease, and it eventually dissipates, though it can still bring heavy rain and flooding as it decays. However, the remnants of a hurricane can sometimes merge with other weather systems and cause significant rain and wind far from the tropics. Hurricanes are most common in late summer and early fall when ocean temperatures are warmest. In the Atlantic, hurricane season officially runs from June through November, with the peak in August and September. Understanding hurricanes and being able to predict their path and intensity is critically important because millions of people live in coastal areas that are vulnerable to these storms. Modern weather satellites and computer models have greatly improved forecasters' ability to predict where a hurricane will go, giving people time to evacuate and prepare. But predicting exactly how strong a hurricane will become is still challenging because it depends on many factors, including sea surface temperature, wind shear, and the storm's internal structure. Now let's shift from tropical storms to winter weather. Snow is something many people experience, and it's a beautiful and fascinating phenomenon. Snow forms in clouds when the temperature is below freezing and moisture condenses directly into ice crystals instead of liquid water droplets. These ice crystals grow as more water vapor deposits onto them, forming intricate six-sided snowflakes. The exact shape of a snowflake depends on the temperature and humidity in the cloud as it forms. Different conditions create different crystal structures, which is why snowflakes have so many varied and beautiful patterns. The saying that no two snowflakes are alike is essentially true because the path each crystal takes through the cloud is unique, exposing it to slightly different conditions, and those conditions affect its growth. For snow to reach the ground, the temperature must be at or below freezing not just in the cloud, but also all the way down to the surface. If the air near the ground is above freezing, the snowflakes will melt and fall as rain instead. This is why the temperature, around 32 degrees Fahrenheit, is critical for determining whether you get rain or snow. Sometimes you get a mix, with some precipitation falling as snow and some as rain, or you get sleet, which is rain that freezes into ice pellets as it falls through a layer of cold air near the surface. Freezing rain is particularly treacherous. This happens when rain falls through a thin layer of freezing air right at the surface and lands on surfaces that are below freezing. The raindrops freeze instantly on contact, coating everything with a layer of ice. This can make roads incredibly dangerous and can bring down power lines and tree branches under the weight of the ice. Snowstorms can range from light flurries that barely dust the ground to massive blizzards that bury entire regions under feet of snow. A blizzard is defined not just by the amount of snow, but by wind and visibility. To be officially classified as a blizzard, a storm must have sustained winds of at least 35 miles per hour and visibility reduced to less than a quarter mile for at least 3 hours. Blizzards are incredibly dangerous because the combination of heavy snow, strong wind, and poor visibility makes it easy to become disoriented and lost, even in familiar areas. The wind in a blizzard also creates extreme wind chills, making frostbite and hypothermia serious threats. Some of the worst blizzards in history have paralyzed entire cities and caused numerous deaths. Lake effect snow is a special type of snowstorm that occurs downwind of large lakes, most famously the Great Lakes in North America. In late fall and early winter, the lakes are still relatively warm because water holds heat much longer than land. When cold Arctic air moves across the lakes, the air is warmed and picks up moisture from the lake surface. This warm, moist air then rises and forms clouds. When the air reaches the downwind shore and moves over land, it cools and dumps its moisture as snow. Lake effect snow can be incredibly intense and localized, with some areas receiving several feet of snow while areas just a few miles away see nothing. Cities like Buffalo, New York, are notorious for lake effect snow, sometimes receiving over 100 inches in a single winter. Ice storms occur when freezing rain falls for an extended period, accumulating a thick coating of ice. These storms can be more devastating than snowstorms because the ice is so heavy and sticks to everything. Power lines weigh down and snap under the weight, tree branches crack and fall, and roads become skating rinks. During a severe ice storm, power can be out for days or even weeks as crews work to repair the damage. Let's talk about tornadoes, which are among the most violent and terrifying weather phenomena on Earth. A tornado is a rapidly rotating column of air that extends from a thunderstorm cloud down to the ground. Tornadoes can have wind speeds exceeding 200 miles per hour in the most extreme cases, and they can cause complete destruction along their path. The width of a tornado can vary from just a few yards to more than a mile, and they can travel along the ground for just a few seconds or for many miles over more than an hour. Understanding how tornadoes form is complex, but the basic ingredients are well known. You need a thunderstorm, and not just any thunderstorm, but a special type called a supercell. A supercell is a thunderstorm with a deep, rotating updraft called a mesocyclone. This rotation is key to tornado formation. To understand how rotation develops in a thunderstorm, we need to think about wind shear, which is a change in wind speed or direction with height. Imagine a layer of air near the ground where the wind is blowing from the south at 10 miles per hour, and a layer of air higher up where the wind is blowing from the south at 40 miles per hour. This difference in speed with height creates what's called horizontal wind shear. Now imagine a tube of air lying horizontally in this wind shear. The faster wind on top and slower wind on the bottom would cause this tube to rotate around its horizontal axis, like a rolling pin. If a strong updraft in a thunderstorm lifts one end of this rotating tube, it tips the rotation from horizontal to vertical. Now you have a vertically rotating column of air inside the thunderstorm, and this is the mesocyclone. Not all mesocyclones produce tornadoes, but all tornadoes in supercells come from mesocyclones. The exact process by which the mesocyclone spawns a tornado at the ground is still not completely understood, and it's an active area of research. Scientists believe it involves the interaction between the mesocyclone and small-scale features in the storm, such as the rear flank downdraft, which is a region of sinking air on the backside of the storm. This downdraft wraps around the mesocyclone and may help tighten and intensify the rotation near the ground. When conditions are just right, the rotation tightens into a narrow funnel that extends downward from the cloud base. When this funnel touches the ground, it becomes a tornado. The visible funnel itself is made of condensed water droplets, similar to a cloud, and often debris picked up from the ground. The actual wind is invisible, but you can see its effects as the tornado tears through structures and vegetation. Tornadoes are rated on the enhanced Fujita scale, which ranges from EF0 to EF5, based on the damage they cause. An EF0 tornado has winds of 65 to 85 miles per hour and causes light damage, such as breaking branches and damaging roof shingles. An EF5 tornado has winds exceeding 200 miles per hour and causes incredible damage, completely leveling well-built homes and even tearing up pavement. Fortunately, EF5 tornadoes are extremely rare. Most tornadoes are EF0 or EF1, causing relatively minor damage, but even a weak tornado can be deadly if it catches people off guard. Tornadoes occur most frequently in the central United States in an area known as Tornado Alley, which includes parts of Oklahoma, Kansas, Nebraska, and northern Texas. This region sees hundreds of tornadoes every year, primarily in spring and early summer. The reason Tornado Alley gets so many tornadoes is because it's where different air masses collide. Warm, moist air from the Gulf of Mexico flows northward and meets cool, dry air from Canada and warm, dry air from the deserts of the southwest. The Rocky Mountains to the west create wind shear as air flows over and around them. All these factors come together to create perfect conditions for severe thunderstorms and tornadoes. Tornadoes can occur in other parts of the world as well, but nowhere experiences them as frequently as the United States. One of the most dangerous aspects of tornadoes is their unpredictability. Even with modern radar and forecasting techniques, meteorologists can usually only provide a warning of a few minutes to perhaps half an hour before a tornado strikes. This is because tornadoes develop quickly, and the conditions that lead to tornado formation can change rapidly. Weather radar can detect rotation inside a storm, which is a warning sign, but not every rotating storm produces a tornado. Storm chasers and trained spotters provide valuable ground truth, reporting what they see so forecasters can issue warnings for specific areas. If you're ever in an area under a tornado warning, the safest place to be is in a basement or an interior room on the lowest floor of a sturdy building, away from windows. Mobile homes are particularly dangerous in tornadoes because they can be lifted and destroyed even by relatively weak tornadoes. Now let's consider another fascinating aspect of weather: the water cycle. Everything we've talked about so far, clouds, rain, snow, storms, all of it is part of a grand cycle in which water moves between the ocean, the atmosphere, and the land in a continuous loop. The water cycle is driven by energy from the sun and by gravity. Let's follow a molecule of water through the cycle. It starts in the ocean, which contains about 97% of all the water on Earth. The sun's energy heats the ocean surface, causing water molecules to evaporate, changing from liquid water into invisible water vapor in the air. This water vapor rises into the atmosphere, carried by rising air currents. As it rises, it cools, and when it cools enough, it condenses into tiny liquid droplets, forming clouds. These droplets are so small that they stay suspended in the air, carried by gentle updrafts, but they collide and merge with other droplets, growing larger. Eventually, they become too heavy to stay aloft, and they fall as precipitation, either rain or snow depending on the temperature. Some of this precipitation falls back into the ocean, completing a very short cycle. But some falls on land. When rain falls on land, several things can happen. Some of it evaporates right back into the air, especially if it falls on hot pavement or dry soil. Some of it is taken up by plants, which use it for growth and then release it back into the air through their leaves in a process called transpiration. Transpiration is essentially evaporation from plants. Together, evaporation and transpiration are called evapotranspiration, and they return a huge amount of water to the atmosphere. Some of the rain soaks into the soil, where it can be stored or can percolate down through layers of rock and soil to become groundwater. Groundwater can stay underground for thousands of years, or it can flow slowly towards streams and rivers. Some of the rain flows over the surface as runoff, collecting in streams and rivers that eventually carry it back to the ocean. And so the cycle continues, over and over, without beginning or end. Water is constantly moving through this cycle, changing form from liquid to gas to solid and back again, but the total amount of water on Earth remains essentially constant. The water you drink today might once have been part of a cloud over the Pacific Ocean, or it might have been drunk by a dinosaur millions of years ago. Water is constantly recycled. The water cycle is crucial for life on Earth. It distributes fresh water across the planet, replenishes rivers and lakes, fills aquifers that we tap for drinking water, and moderates climate by transporting heat energy from one place to another. When water evaporates, it absorbs heat energy from its surroundings, cooling them. When it condenses, it releases that heat energy, warming the air around it. This transport of energy is a major factor in weather and climate. Hurricanes, as we discussed, are essentially heat engines powered by the evaporation and condensation of ocean water. Even ordinary rainstorms involve this transfer of heat. Evaporation from the warm surface carries heat upward, and when the water vapor condenses high in the atmosphere, it releases that heat into the upper air. Let's think about how all of this connects to climate, which is different from weather. Weather is what's happening right now. The day-to-day variations in temperature, precipitation, wind, and clouds. Climate is the long-term average of weather over many years, typically at least 30 years. Climate tells you what to expect on average. If you live in a tropical climate, you expect it to be warm year-round with a lot of rain. If you live in a desert climate, you expect it to be dry with very little rain. But the actual weather on any given day can vary significantly from the climate average. You can have an unusually cold day in a warm climate, or a rainy day in a dry climate. The climate is the average tendency. The weather is the specific realization on a particular day. Earth's climate is determined by the same factors that drive weather: the distribution of solar energy, the composition of the atmosphere, the circulation of air and water, and the features of Earth's surface like oceans, mountains, and ice caps. Over very long time scales, Earth's climate has changed dramatically. There have been ice ages when glaciers covered much of North America and Europe, and there have been warm periods when there was little or no ice even at the poles. These changes happen because of shifts in Earth's orbit, changes in the sun's output, volcanic eruptions that inject particles into the atmosphere, and changes in the concentration of greenhouse gases in the atmosphere. Greenhouse gases, like carbon dioxide, methane, and water vapor, trap heat in the atmosphere. They allow sunlight to pass through and warm the surface, but they absorb the infrared radiation that the surface emits, trapping that heat and keeping the planet warmer than it would be otherwise. Without the natural greenhouse effect, Earth would be about 60 degrees Fahrenheit colder than it is, too cold for liquid water to exist on the surface. However, the concentration of greenhouse gases can change, and when it does, the climate changes too. More greenhouse gases mean more heat is trapped and the planet warms. Fewer greenhouse gases mean less heat is trapped and the planet cools. Over the past century, human activities, particularly the burning of fossil fuels like coal, oil, and natural gas, have increased the concentration of carbon dioxide in the atmosphere by about 50%. This is enhancing the greenhouse effect and causing the planet to warm. This warming affects weather patterns in complex ways. Warmer air can hold more moisture, which can lead to heavier rainfall events. Warmer oceans provide more energy for hurricanes, potentially making them more intense. Changes in temperature patterns can shift the jet stream and alter where storms occur. Some regions may become wetter, others drier. Understanding how climate change affects weather is an area of intense research because it has profound implications for agriculture, water resources, sea level, and human society. But let's return to the everyday experience of weather and talk about some phenomena you might have seen but never quite understood. Rainbows, for instance, are a beautiful and common sight, yet the physics behind them is elegant. A rainbow appears when sunlight and rain happen at the same time, and you're positioned between the sun and the rain with the sun behind you. Sunlight is made up of all the colors of the spectrum mixed together, which is why it appears white. When sunlight enters a raindrop, it slows down and bends, a process called refraction. Different colors bend by different amounts because they have different wavelengths. Red light bends the least, and violet light bends the most. After entering the raindrop, the light reflects off the inside back surface of the drop and then exits the drop, bending again as it does. This double bending and the reflections separate the white light into its component colors. The light exits the raindrop at different angles depending on the color. Red light exits at a steeper angle than violet light. When you look at the sky with the sun behind you, you see different colors coming from droplets at different angles. The red light comes from droplets higher in the sky, and the violet light from droplets lower in the sky, with the other colors, orange, yellow, green, blue, indigo, in between. This creates the arc of colors we call a rainbow. The arc is actually part of a circle, and if you were high enough, like in an airplane, you could see the full circle. Each raindrop only sends one color to your eye, but there are millions of raindrops, so you see the full spectrum arrayed across the sky. Sometimes you see a double rainbow, with a fainter second rainbow above the primary one. The secondary rainbow is caused by light that reflects twice inside the raindrops before exiting. This extra reflection reverses the order of colors, so in the secondary rainbow, red is on the inside and violet is on the outside. The area between the primary and secondary rainbows often appears darker than the sky around them. This dark band is called Alexander's band, named after the ancient Greek philosopher Alexander of Aphrodisias, who first described it. The reason it's darker is because very little light exits the raindrops at the angles corresponding to this region. Another optical phenomenon you might see is a halo around the sun or moon. Unlike rainbows, which are caused by water droplets, halos are caused by ice crystals in high thin clouds called cirrus clouds. These ice crystals are typically hexagonal in shape, like tiny prisms. When light passes through these crystals, it bends and spreads into a ring around the sun or moon. The most common halo is a circle with a radius of 22 degrees, which is about the width of your outstretched hand held at arm's length. Halos are often a sign that a weather change is coming, because cirrus clouds typically precede a warm front and the rain or snow that comes with it. So if you see a halo around the moon at night, there's a reasonable chance it will rain or snow within the next day or so. Sundogs are another ice crystal phenomenon. They appear as bright spots on either side of the sun, usually at the same height as the sun. Like halos, they're caused by light refracting through hexagonal ice crystals in cirrus clouds. But only crystals that are oriented in a specific way create sundogs. The name comes from the idea that the bright spots seem to follow the sun like faithful dogs. Sundogs are often quite colorful, with red on the side closest to the sun and blue farther out. Lightning, which we've mentioned briefly, is worth exploring in more detail because it's one of the most powerful and dramatic events in nature. A typical lightning bolt carries about 30,000 amperes of current, compared to a household circuit breaker that trips at 15 or 20 amperes. The voltage can be hundreds of millions of volts. This enormous electrical discharge happens in a fraction of a second. A lightning bolt is actually a series of events that happen very quickly. It starts with a stepped leader, which is a channel of ionized air that reaches down from the cloud toward the ground, in steps of about 50 meters at a time. The stepped leader is relatively faint and invisible to the naked eye. When it gets close to the ground, the electric field becomes so strong that a streamer of positive charge reaches up from the ground or from tall objects like trees or buildings to meet it. When the leader and the streamer connect, a circuit is completed, and a powerful return stroke of current surges up from the ground into the cloud along the path the leader created. This return stroke is the bright flash you see as lightning. Often, there are multiple strokes along the same channel, so the lightning appears to flicker. All of this happens in less than a second. The intense heat of the lightning, which can reach 50,000 degrees Fahrenheit, causes the air to expand explosively, creating the shock wave we hear as thunder. Thunder itself is fascinating. The sound can tell you how far away the lightning is. Light travels so fast that you see the lightning essentially instantly, but sound travels much slower, about 1 mile every 5 seconds. So if you count the seconds between seeing the lightning and hearing the thunder and divide by 5, you get the distance to the lightning strike in miles. If you hear thunder less than 30 seconds after seeing lightning, the storm is close enough to be dangerous, and you should seek shelter immediately. Lightning can strike from a storm cloud that's 10 miles away, sometimes even appearing to come out of a blue sky. This is called a bolt from the blue, and it happens when a lightning bolt travels horizontally through the upper atmosphere for miles before descending to the ground. Lightning is incredibly dangerous. It kills dozens of people every year and injures hundreds more. If you're caught outside in a thunderstorm, the safest thing to do is get inside a building or a hard-topped vehicle. If you can't get to shelter, avoid open areas, tall isolated trees, and bodies of water. Don't lie flat on the ground. Instead, crouch down with your feet together and your head down, minimizing your contact with the ground. If you're in a group, spread out so that if lightning strikes, it doesn't affect everyone. Inside a building, stay away from windows, avoid using landline phones, and don't take a shower or bath during a thunderstorm because plumbing can conduct electricity. Lightning also comes in different forms. The most common is cloud-to-ground lightning, which we've been discussing. But there's also intra-cloud lightning, which occurs within a single cloud, and intercloud lightning, which jumps from one cloud to another. You see these as flickers of light within the clouds during a storm, often called sheet lightning. There's also a rare and mysterious form called ball lightning, which eyewitnesses describe as a glowing sphere that floats through the air. Ball lightning is not well understood because it's so rare and appears unpredictably, making it difficult to study scientifically. Some scientists question whether it even exists, but there have been enough credible reports that it's taken seriously as a real, if poorly understood, phenomenon. Let's talk about the seasons in more detail and how they affect not just temperature, but the entire character of the weather. In spring, the sun is climbing higher in the sky, and days are getting longer. The ground and oceans are still cool from winter, but the air is warming. This creates a clash between lingering cold air and advancing warm air, leading to a very active pattern of weather. Spring is the prime season for severe thunderstorms and tornadoes in many regions because the strong temperature contrasts and increasing solar heating provide the energy and instability needed for these storms. Spring also brings rain, as storm systems track across the continents, watering the land and bringing everything back to life after winter. In many places, spring is the wettest season. As spring transitions to summer, the sun reaches its highest point in the sky and days are longest. The land heats up and warm, humid air masses dominate. Thunderstorms are common, particularly in the afternoon when solar heating is strongest. In some regions, summer brings a monsoon, which is a seasonal shift in wind patterns that brings heavy rain. The classic monsoon occurs in South Asia, where the summer heating of the land creates a strong low-pressure area that draws in moist air from the Indian Ocean, bringing months of heavy rain. Similar monsoon patterns occur in other parts of the world, including West Africa, Northern Australia, and the southwestern United States. The summer monsoon is crucial for agriculture in these regions, providing the water needed to grow crops. As summer fades into fall, the sun gets lower in the sky and days shorten. The air begins to cool, but the oceans and land are still warm from summer, creating another period of temperature contrasts. Fall can be a beautiful season, with comfortable temperatures and often stable weather, especially in the early part of the season. But it's also when hurricanes peak in the Atlantic, fueled by the warm ocean waters. As fall progresses, the temperature contrasts sharpen, and storm systems become more frequent and intense. The jet stream, which shifted northward in summer, begins to move southward again, bringing the first blasts of cold air, and sometimes the first snow of the season. Winter is the season of cold, and in many places, snow. The sun is at its lowest in the sky, and days are shortest. The land cools rapidly, and in the higher latitudes, snow and ice cover the ground, reflecting sunlight back into space and making it even colder. Arctic air masses plunge southward, bringing bitter cold and strong winds. Winter storms develop along the boundaries between these cold air masses and warmer air, bringing snow, ice, and wind. In the coldest regions, temperatures can drop to -40 degrees or lower, cold enough that exposed skin can freeze in minutes. Yet winter has its own stark beauty, with snow-covered landscapes and clear, crisp air. And of course, winter eventually gives way to spring, and the cycle begins anew. Different parts of the world experience these seasons differently. In the tropics, temperature changes little throughout the year, but there are wet and dry seasons driven by shifts in rainfall patterns. In the Mediterranean climate, summers are hot and dry, while winters are mild and wet, the opposite of what happens in continental climates. In polar regions, the variation is extreme, with continuous daylight in summer and continuous darkness in winter, and temperatures that range from relatively mild in summer to incredibly cold in winter. Understanding these regional patterns is part of what makes weather and climate so endlessly fascinating. No two places are exactly alike, and each has its own rhythm and character. Now let's think about some of the more unusual weather phenomena that occur around the world. Dust storms, for example, are common in arid regions where there's loose, dry soil and strong winds. A dust storm occurs when wind picks up dust and sand from the ground and carries it into the air, sometimes creating a wall of dust thousands of feet high that can travel for hundreds of miles. The dust reduces visibility to near zero and can cause respiratory problems. In the Sahara Desert, dust storms are so large that they carry dust all the way across the Atlantic Ocean to South America and the Caribbean, where the dust settles and actually provides nutrients to the soil and ocean. In the southwestern United States, dust storms are called haboobs, an Arabic word. These storms typically form along the outflow boundary of a dying thunderstorm, where the cool downdraft air spreads out along the ground, picking up dust as it goes. Waterspouts are tornadoes that form over water. They're most common over warm tropical waters and are generally weaker than their land-based counterparts, though they can still be dangerous to boats and swimmers. A waterspout looks like a funnel of spray extending from a cloud down to the water surface. Some waterspouts form in the same way as tornadoes, from supercell thunderstorms, but many form in a different way, from rapidly building cumulus clouds over warm water. These fair-weather waterspouts are usually brief and weak. Microbursts are another dramatic phenomenon. A microburst is a small area of very strong downdraft in a thunderstorm. When the downdraft hits the ground, it spreads out in all directions, creating winds that can exceed 100 miles per hour over an area less than 2.5 miles across. Microbursts are extremely dangerous to aircraft because they create wind shear, a sudden change in wind speed and direction. Several airplane crashes have been caused by microbursts, leading to better detection systems and pilot training. On the ground, a microburst can cause damage that looks similar to tornado damage, with trees knocked down in a radial pattern rather than the circular pattern of a tornado. Fire weather is a term for conditions that promote wildfires, including high temperatures, low humidity, and strong winds. In many regions, especially in the western United States, Mediterranean areas, and Australia, fire weather is a serious concern during dry seasons. Lightning from thunderstorms can ignite fires, but so can human activities. Once a fire starts in dry, windy conditions, it can spread rapidly and become almost impossible to control. Large wildfires can create their own weather, generating powerful updrafts that lift smoke and embers high into the atmosphere. These updrafts can be strong enough to generate fire tornadoes, which are whirling columns of flame and smoke that move across the landscape. Wildfires also produce enormous amounts of smoke and particulates that can degrade air quality hundreds of miles away. Inversions are another interesting atmospheric phenomenon. Normally, temperature decreases as you go higher in the atmosphere, but sometimes a layer of warm air forms above a layer of cooler air, creating a temperature inversion. Inversions can trap pollution near the surface because the warm air acts like a lid, preventing the cooler air below from rising and dispersing pollutants. This is why cities in valleys like Los Angeles or Mexico City can have severe air pollution problems. The surrounding mountains trap the air, and an inversion prevents it from mixing upward. Let's consider the role of mountains in weather. Mountains have a profound effect on climate and weather patterns. When moist air approaches a mountain range, it's forced to rise. As it rises, it cools and its moisture condenses, forming clouds and precipitation on the windward side of the mountain, the side facing the wind. This is called orographic lift. The air that passes over the mountain and descends the other side warms up and dries out, creating a rain shadow on the leeward side. The leeward side receives much less precipitation than the windward side, and this can create dramatically different climates over short distances. The western slopes of the Cascade Range and the Rocky Mountains receive abundant rain and snow, while just a few dozen miles to the east, the land is much drier. Many of the world's deserts are in the rain shadows of mountain ranges. Downslope winds are strong winds that blow down the leeward side of a mountain. As air descends, it compresses and warms. If it's started very high and descends a long way, it can become quite warm by the time it reaches the valley below. These warm, dry downslope winds go by different names in different parts of the world. In the Rocky Mountains, they're called Chinook winds. In the Alps, they're called Foehn winds. In Southern California, they're called Santa Ana winds. These winds can cause temperatures to rise dramatically, sometimes by 30 or 40 degrees in just a few hours. They also dry out vegetation, increasing fire danger. The ocean plays a critical role in weather and climate, not just because it's a source of moisture, but because water has a very high heat capacity. This means it takes a lot of energy to change the temperature of water. The ocean can absorb enormous amounts of heat without warming up much, and it can release that heat without cooling down much. This makes the ocean a giant thermal reservoir that moderates climate. Coastal areas have milder climates than inland areas at the same latitude because the ocean keeps temperatures from getting too hot in summer or too cold in winter. The ocean also has currents, large-scale flows of water driven by wind, the Earth's rotation, and differences in water density. These currents transport heat around the planet. The Gulf Stream, for example, carries warm water from the Gulf of Mexico northward along the eastern coast of the United States, and then across the Atlantic to Europe. This warm water keeps northern Europe much warmer than it would otherwise be. Places like Ireland and Scotland are at the same latitude as Labrador in Canada, but they have much milder climates because of the Gulf Stream's warmth. Ocean currents can also influence weather on shorter timescales. El Niño and La Niña are opposite phases of a climate pattern in the tropical Pacific Ocean that affects weather around the world. Under normal conditions, trade winds blow from east to west across the tropical Pacific, pushing warm surface water toward the western Pacific near Indonesia and the Philippines. This allows cooler water to well up along the coast of South America. During El Niño, the trade winds weaken or even reverse, and the warm water sloshes back toward the east, spreading across the central and eastern Pacific. This shift in ocean temperature changes the position of rising air and affects the jet stream, which in turn affects weather patterns globally. El Niño tends to bring wetter conditions to the southern United States and South America, and drier conditions to Indonesia and Australia. La Niña is the opposite pattern, with stronger trade winds and cooler than normal water in the eastern Pacific, and it tends to have opposite effects on weather. El Niño and La Niña events occur irregularly, every 2 to 7 years, and can last for several months to a couple of years. Atmospheric rivers are another fascinating phenomenon related to moisture transport. These are long, narrow bands of intense moisture in the atmosphere, typically a few hundred miles wide and over 1,000 miles long. They form when winds concentrate moisture from the tropics into a narrow flow, like a river in the sky. When an atmospheric river makes landfall, it can dump enormous amounts of rain in a short time, sometimes leading to flooding. Atmospheric rivers are responsible for much of the precipitation that falls on the west coasts of continents in the mid-latitudes. In California, a few atmospheric river events each winter can provide much of the water supply for the year, but they can also cause devastating floods if they're too intense or if several occur in quick succession. Understanding weather forecasting is something many people are curious about. How do meteorologists predict what the weather will be like tomorrow or next week? The short answer is that they use computer models. These models are incredibly complex programs running on some of the most powerful supercomputers in the world. The basic idea is to represent the atmosphere mathematically. The atmosphere follows the laws of physics, and those laws can be written as equations. Temperature, pressure, humidity, wind, all of these can be described by equations that relate them to each other and show how they change over time. The computer divides the atmosphere into a three-dimensional grid of boxes, maybe 20 miles on a side and a mile tall. For each box, the model calculates the temperature, pressure, humidity, wind speed and direction, and other variables. Then it uses the equations of physics to calculate how those values will change over the next few minutes. It does this calculation for every single box in the grid, which might be millions of boxes covering the entire planet. Then it advances time by a few minutes and does all the calculations again, over and over, stepping forward in time to predict the future state of the atmosphere. This sounds straightforward, but it's enormously complicated. The equations are complex and interconnected. A change in one box affects the boxes around it, and those affect others, and so on. Small errors can grow rapidly. This is why weather forecasts become less accurate the farther out you go. A forecast for tomorrow is usually quite accurate. A forecast for a week from now is less reliable. A forecast for 2 weeks from now is only marginally better than guessing. The atmosphere is a chaotic system, which means small differences in initial conditions can lead to very different outcomes. This is the famous butterfly effect, the idea that a butterfly flapping its wings in Brazil could theoretically set off a chain of events that leads to a tornado in Texas weeks later. While that's an exaggeration, the underlying principle is real. Tiny uncertainties in our measurements of current conditions grow over time, limiting how far into the future we can make useful predictions. To deal with this uncertainty, meteorologists run ensemble forecasts. Instead of running the model just once with one set of initial conditions, they run it many times, maybe 50 or 100 times, each time with slightly different initial conditions. These different runs produce different forecasts, and by looking at all of them together, forecasters can get a sense of how confident they should be in the prediction. If all the runs show rain tomorrow, you can be very confident it will rain. If half show rain and half show sunshine, the forecast is much less certain. Ensemble forecasting has greatly improved weather prediction over the past few decades. Weather models also need data, lots of data, about the current state of the atmosphere. This data comes from thousands of sources around the world. Weather stations on the ground measure temperature, pressure, humidity, wind, and precipitation. Weather balloons launched twice a day from hundreds of locations around the world carry instruments up through the atmosphere, measuring conditions at different heights. Commercial aircraft report temperature and wind data from their flight paths. Buoys floating in the ocean measure sea surface temperature and wave conditions. And perhaps most importantly, Satellites orbiting the Earth provide continuous observations of cloud cover, temperature, humidity, wind, and many other variables over the entire planet, including remote areas like the oceans and polar regions, where ground-based observations are sparse. All this data is collected and fed into the models to give them the most accurate possible picture of current conditions. Without satellites, modern weather forecasting would be vastly less accurate, especially beyond a day or two. Different weather models exist, and they sometimes disagree with each other. The American model, called the GFS, covers the entire globe. The European model, called the ECMWF, is generally considered the most accurate global model. There are also regional models that focus on smaller areas with finer detail. Meteorologists look at all the available models and use their expertise and understanding of local conditions to make the final forecast. This is why meteorology is still as much an art as a science. The models provide guidance, but a skilled forecaster adds value by interpreting the models and knowing when to trust them and when to be skeptical. Despite all these advances, some weather events remain difficult to predict. Exactly where and when a tornado will touch down is still nearly impossible to forecast more than a few minutes in advance. Whether a thunderstorm will produce damaging hail or just rain is uncertain. How much snow will fall from a winter storm can vary widely depending on small shifts in the storm's track or intensity. And precipitation amounts are always uncertain because the models have difficulty representing the small-scale processes that produce rain and snow. This is why you sometimes see a forecast for a 30% chance of rain. It doesn't mean it will rain for 30% of the day. It means there's a 30% probability that it will rain at all at your location. This probabilistic forecasting is a way of communicating uncertainty, and it's more honest than just saying it will or won't rain when the situation is genuinely uncertain. Let's talk about some extreme weather records to give you a sense of just how variable and intense weather can be. The highest temperature ever reliably recorded on Earth was 134 degrees Fahrenheit in Death Valley, California, in July 1913. Death Valley is one of the hottest places on Earth because it's a deep desert basin surrounded by mountains that trap heat. The lowest temperature ever recorded was -128.6 degrees Fahrenheit at Vostok Station in Antarctica in July 1983. Antarctica is incredibly cold because it's covered by a thick ice sheet at high elevation, and during the polar winter, there's no sunlight for months to provide any warmth. The coldest temperature ever recorded outside of Antarctica was -96 degrees Fahrenheit in Oymyakon, Russia, a village in Siberia that's one of the coldest permanently inhabited places on Earth. Imagine living somewhere where winter temperatures routinely drop below -60 degrees. The wettest place on Earth, in terms of average annual rainfall, is Mawsyn Rum, India, which receives about 467 inches of rain per year on average. That's nearly 40 feet of rain. This incredible rainfall is due to the monsoon, as moist air from the Bay of Bengal is lifted by the Himalayan foothills, causing torrential rains. The driest place on Earth is the Atacama Desert in Chile, where some locations have never recorded any rainfall in the entire time measurements have been kept. The Atacama is dry because it's in the rain shadow of the Andes Mountains to the east, and cold ocean currents offshore suppress evaporation and rainfall. The fastest wind ever recorded, not in a tornado, was during Tropical Cyclone Olivia in 1996 on Barrow Island, Australia, where a gust of 253 miles per hour was measured. Inside tornadoes, winds are estimated to exceed 300 miles per hour in the strongest cases, but these are estimates because anemometers, the instruments that measure wind, are destroyed when a violent tornado hits. The most rain ever recorded in a single day was 73.6 inches at Foxok on the island of Reunion in the Indian Ocean during a tropical cyclone in 1966. The most snow from a single storm in the United States was 189 inches at Mount Shasta Ski Bowl in California in February 1959. and the largest hailstone ever recorded in the United States fell in Vivian, South Dakota in July 2010. It was 8 inches in diameter and weighed nearly 2 pounds. Imagine something that size falling from the sky. These extremes show the incredible range of conditions that Earth's atmosphere can produce. But for most people, most of the time, weather is far less dramatic. It's the gentle rain that waters your garden, the pleasant breeze on a spring day, the snow that falls quietly at night. Even ordinary weather is the result of the same physical processes that create the extremes. It's all part of the same system, driven by the sun's energy, Earth's rotation, and the properties of air and water. Weather affects every aspect of human life. It determines what crops can grow and when they can be planted and harvested. It affects transportation, grounding flights, closing roads, and making travel dangerous. It influences our mood and health. Some people experience seasonal affective disorder, a type of depression that occurs during the winter months when days are short and sunlight is scarce. Weather determines what we wear, what activities we can do, and even what we eat. Entire industries are built around predicting and responding to weather, from agriculture to aviation to energy production. On hot summer days, air conditioning drives electricity demand to its peak. On cold winter days, heating does the same. Utilities must anticipate these demands and ensure they have enough generating capacity. Weather also has a profound impact on history. Storms have sunk fleets and altered the course of wars. The Mongol invasions of Japan in the 13th century were thwarted twice by typhoons that destroyed the invasion fleets, events the Japanese called kamikaze, or divine wind. The Spanish Armada's attempt to invade England in 1588 was defeated partly by storms that scattered and sank many ships. Napoleon's invasion of Russia in 1812 and Hitler's invasion in 1941 both failed in part because of the brutal Russian winter. Weather has shaped where people live, with most of the world's population concentrated in temperate zones with moderate climates. And weather disasters, droughts, floods, famines caused by crop failures, have driven mass migrations throughout history. Understanding weather helps us prepare for and adapt to it. Farmers time their planting based on climate patterns and weather forecasts. Cities build drainage systems to handle expected rainfall. Coastal communities build defenses against storm surge. People in tornado-prone areas have storm shelters. In places where hurricanes are common, building codes require structures to withstand high winds. These adaptations save lives and reduce damage, but they require knowledge of what weather to expect. Let's think about the role of clouds in more detail, because clouds are one of the most visible and varied aspects of weather. We've talked about cumulus clouds, those puffy fair weather clouds, and about thunderstorm clouds. But there are many other types. Clouds are classified based on their height in the atmosphere and their appearance. Low clouds form below about 6,000 feet. Middle clouds form between 6,000 and 20,000 feet. High clouds form above 20,000 feet. The names come from Latin. Cirrus means curl or wisp. Cumulus means heap or pile. Stratus means layer or spread out. Nimbus means rain. These terms are combined to name different cloud types. Cirrus clouds are high, thin, wispy clouds made of ice crystals. They often look like streaks or curls painted across the sky. Cirrus clouds usually indicate fair weather, but they can also be the first sign of an approaching storm system, forming ahead of a warm front. Cirrostratus clouds are high, thin layers that can cover the entire sky, creating a milky or hazy appearance. They're also made of ice crystals and often produce halos around the sun or moon. Cirrocumulus clouds are high clouds that appear as small, white patches or ripples, sometimes called a mackerel sky, because the pattern resembles the scales on a mackerel fish. These clouds are less common than cirrus or cirrostratus. At middle levels, we have altocumulus clouds, which are grayish-white clouds that appear as rounded masses or rolls, often in parallel bands. They usually indicate fair weather but can develop into thunderstorms if the atmosphere becomes unstable. Altostratus clouds are gray or blue-gray layers that cover the sky. The sun or moon can usually be seen through altostratus, but only dimly, like through frosted glass. These clouds often form ahead of storms with continuous rain or snow. Low clouds include stratus, which is a uniform gray layer that often covers the entire sky, like a gray blanket. Stratus can produce drizzle or light snow. Fog is essentially stratus at ground level. Stratocumulus clouds are low, lumpy clouds that appear in rows or patches. They're thicker than stratus and can produce light rain. Nimbostratus is a dark, thick, shapeless layer that produces continuous rain or snow. The word nimbus indicates that it's a rain cloud. Cumulus clouds, which we've discussed, come in different varieties. Fair weather cumulus are small, puffy, and indicate stable conditions. Cumulus congestus are larger, towering cumulus that are growing taller and may develop into thunderstorms. Cumulonimbus are the full-fledged thunderstorm clouds, towering monsters that can reach 40,000 feet or higher, with anvil-shaped tops where they spread out against the stratosphere. These clouds produce heavy rain, lightning, hail, and sometimes tornadoes. Clouds are beautiful and endlessly varied. The same type of cloud can look different depending on the time of day, the angle of sunlight, and the weather conditions. Sunrise and sunset paint clouds in brilliant oranges, pinks, and reds. Storm clouds can be dark and ominous or dramatic and inspiring. Watching clouds is a simple pleasure that connects us directly to the weather and the processes happening in the atmosphere above us. Let's consider precipitation in more detail. We've talked about rain, snow, and hail, but there are other forms as well. Drizzle is very light rain with droplet sizes smaller than regular rain. Drizzle usually falls from stratus clouds and doesn't accumulate much. Freezing drizzle occurs when drizzle falls through a layer of air that's below freezing and freezes on contact with surfaces, creating a glaze of ice. Sleet is small ice pellets that form when raindrops freeze as they fall through a layer of cold air. Sleet bounces when it hits the ground and doesn't stick to things the way freezing rain does. Graupel, also called snow pellets, forms when supercooled water droplets freeze onto falling snowflakes, creating soft, crumbly pellets. Graupel is common in winter storms and is sometimes mistaken for hail, but it's much softer and lighter. The amount of precipitation that falls is measured with a rain gauge, which is simply a container that catches rain or melted snow and measures the depth. Standard rain gauges are designed so that the opening is a specific size, allowing for accurate measurement. Automated gauges can measure precipitation continuously and report it in real time. Snow depth is measured with a ruler or measuring stick, but what meteorologists really care about is the water equivalent, how much water is in the snow. Fresh, fluffy snow has a lot of air in it, so it takes about 10 inches of snow to equal 1 inch of rain. Wet, heavy snow has less air, so the ratio might be closer to 5:1. In the mountains, measuring snow is critical for water resource management because snowpack serves as a natural reservoir, storing water during winter and releasing it gradually as it melts in spring and summer. Water managers carefully monitor snowpack to predict how much water will be available for agriculture, drinking water, and hydroelectric power. Precipitation patterns vary widely around the world. In the tropics, most rain falls during the wet season, often in heavy afternoon thunderstorms. In the mid-latitudes, precipitation is more evenly distributed through the year, though there are often wetter and drier seasons. In Mediterranean climates, rain falls primarily in winter, while summers are dry. In monsoon climates, nearly all the year's rain falls during a few months when the monsoon is active. In polar regions, precipitation is sparse and nearly all of it falls as snow. Some places, like tropical rainforests, receive rain almost every day, while others, like deserts, might go years without rain. The variability of precipitation is one of the challenges of water management. Too much rain too quickly causes flooding. Too little rain causes drought. Both extremes can have devastating consequences. Floods can destroy homes, infrastructure, and crops, and they can cause loss of life. Droughts can lead to crop failures, water shortages, and wildfires. Managing water resources requires understanding both the average precipitation and the variability, the likelihood of extremes in either direction. Drought is a prolonged period of below-average precipitation that leads to water shortages. Droughts can last for months or even years. They develop slowly, unlike floods or storms which happen suddenly. A drought might start with a few weeks of dry weather that isn't too concerning, but as the dry conditions persist, soil moisture depletes, stream flows drop, reservoirs shrink, and impacts compound. Agricultural drought affects crops and livestock. Hydrological drought affects water supply in rivers, lakes, and groundwater. Socioeconomic drought occurs when water shortages affect people's ability to live and work. Severe droughts have caused famines throughout history, and even in modern times, they can lead to economic losses and hardship. Flooding is the opposite problem, too much water. Floods can be caused by heavy rain, snowmelt, storm surge from hurricanes, or dam failures. Flash floods are particularly dangerous because they develop rapidly, sometimes in minutes, giving people little time to react. Flash floods often occur in small watersheds where heavy rain falls on steep terrain or on impermeable surfaces like rock or pavement. The water can't soak into the ground, so it runs off quickly, creating a surge that rushes down valleys and canyons. Flash floods can turn a dry creek bed into a raging torrent in minutes. They're the leading cause of weather-related deaths in many countries because people underestimate their power and try to drive or walk through floodwaters. Just 6 inches of fast-moving water can knock you off your feet, and 2 feet of water can carry away a car. River flooding develops more slowly over days or weeks as persistent rain or snowmelt causes rivers to rise above their banks. River floods can inundate vast areas and last for weeks. The Mississippi River flood of 1993 covered parts of 9 states and caused billions of dollars in damage. Coastal flooding from storm surge is another major threat, particularly with hurricanes. The combination of low pressure and strong winds can push water levels 10 or 20 feet above normal flooding coastal areas. Climate and weather are deeply interconnected with the water cycle, the carbon cycle, and energy flows around the planet. Everything is connected in a vast, complex system. Changes in one part of the system can have effects far away. This is why understanding weather requires thinking holistically about the Earth system as a whole, not just looking at individual parts in isolation. Let's talk about some of the myths and misconceptions about weather. One common myth is that lightning never strikes the same place twice. This is completely false. Lightning strikes the Empire State Building in New York City about 25 times per year, and some tall structures have been hit hundreds of times. Lightning takes the path of least resistance, which often means tall, pointed objects. Another myth is that opening windows during a tornado will equalize pressure and prevent your house from exploding. This is false and dangerous. Tornadoes don't make buildings explode from pressure differences, they destroy them with extreme winds. Opening windows just wastes precious time that should be spent getting to shelter. Some people believe that tornadoes never cross rivers or go uphill. This is false. Tornadoes can cross rivers, lakes, mountains, anything. The terrain has little effect on a strong tornado. Another myth is that the southwest corner of a basement is the safest place during a tornado. This came from a misinterpretation of damage statistics and is not true. The safest place is the lowest level of a building, in a small interior room away from windows, regardless of which corner it's in. Some people think you can outrun a tornado in a car. This is extremely dangerous. Tornadoes can change direction unpredictably and can move faster than cars can drive, especially if you're on rural roads. The safest thing to do is get to a sturdy shelter, not try to flee. There's a persistent myth that the Coriolis effect makes water drain counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. While the Coriolis effect is real and does affect large-scale phenomena like hurricanes, it has no noticeable effect on small things like bathtubs or sinks. The direction water drains in your sink is determined by the shape of the basin and the initial motion of the water, not by the Coriolis effect. You can easily demonstrate this by filling your sink and letting it drain multiple times. It won't always spin the same direction. Another misconception is that weather forecasts are usually wrong. In fact, modern forecasts are remarkably accurate, especially for the next few days. Studies show that today's 5-day forecast is as accurate as the 1-day forecast was 30 years ago. Forecasters are right much more often than they're wrong, but people tend to remember the times the forecast was wrong and forget the many times it was right. It's also important to understand what a forecast is saying. A forecast for a 40% chance of rain doesn't mean the forecast is wrong if it doesn't rain. It means there was a 60% chance it wouldn't rain, which is what happened. Some people believe that weather control is possible or is being done secretly. While there are techniques like cloud seeding that can slightly enhance precipitation under certain conditions, we do not have the ability to control or significantly alter the weather. The atmosphere is far too large and complex for humans to control with current technology. Conspiracy theories about chemtrails, the idea that airplane contrails are chemicals being sprayed for nefarious purposes, are false. Contrails are simply condensation trails, clouds formed by water vapor in jet engine exhaust, freezing in the cold upper atmosphere. Weather has inspired art, literature, and culture throughout human history. Countless poems, paintings, songs, and stories feature weather as a central element. Storms represent chaos or divine wrath. Sunshine represents hope and happiness. Rain can symbolize sadness or renewal. The weather is deeply embedded in human consciousness and language. We use weather metaphors constantly without even thinking about it. We talk about brainstorming, weathering a crisis, being under a cloud, having a sunny disposition, feeling under the weather, or waiting for the storm to pass. Different cultures have different relationships with weather. In agricultural societies, weather dominates life, determining when to plant and harvest, and whether the crop will succeed or fail. Traditional knowledge about weather signs, the appearance of certain clouds, the behavior of animals, the color of the sunset, has been passed down through generations. Much of this folk wisdom has a basis in science. For example, the saying, "Red sky at night, sailor's delight, red sky in morning, sailor's warning," has truth to it. A red sky at sunset occurs when the setting sun shines through clear air to the west, lighting up clouds to the east. Since weather systems generally move from west to east, clear skies to the west suggest fair weather is approaching. A red sky in the morning means the sun is shining through clear air to the east, onto clouds in the west, suggesting a storm system is approaching from the west. Another saying is, "Ring around the moon, rain soon." As we discussed, a halo around the moon is caused by ice crystals in cirrus clouds, which often precede a warm front and rain. So there's scientific truth behind this bit of folklore. Other weather lore is less reliable or entirely superstitious, but it shows how important weather has been to human cultures. In modern times, weather has become a major media event. Weather forecasts are a staple of news broadcasts. Weather apps on smartphones give people instant access to forecasts and radar. During severe weather, coverage can become around the clock, with meteorologists tracking storms and providing life-saving information. The professionalization of meteorology and the improvement in forecasting have saved countless lives by giving people advance warning of dangerous weather. Storm chasing has become both a scientific endeavor and a recreational activity. Scientists chase storms to deploy instruments and study them up close, gathering data that helps improve understanding and forecasting. Recreational storm chasers are enthusiasts who pursue the thrill of witnessing nature's power. Storm chasing is dangerous and requires knowledge, experience, and respect for the hazards involved. Every year, people are injured or killed while chasing storms, sometimes because they took unnecessary risks. The wonder of weather is that it's always happening, always changing, always offering something new to observe and learn about. No 2 days are exactly alike. The sky is a constantly shifting canvas. Understanding the science behind weather doesn't diminish its beauty, it enhances it. When you see a thunderstorm approaching and you understand that you're watching the atmosphere's way of redistributing heat and moisture, that the lightning is a massive electrical discharge, that the rain is water that evaporated from the ocean and is now returning to the land, it becomes even more amazing. Weather instruments have evolved tremendously over the centuries, but the basic principles remain the same. A thermometer measures temperature, and the most common type uses the expansion and contraction of a liquid, traditionally mercury or alcohol, in a sealed tube. As temperature rises, the liquid expands and moves up the tube. As temperature falls, it contracts and moves down. Digital thermometers use electronic sensors that change their electrical resistance with temperature, and these can be much more precise. A barometer measures air pressure. The traditional mercury barometer uses a column of mercury in a tube. The weight of the atmosphere pushes down on a reservoir of mercury, forcing mercury up into the tube. Higher pressure pushes it higher, lower pressure lets it fall. Changes in pressure can indicate changing weather. Rising pressure often means improving weather, while falling pressure often means a storm is approaching. Aneroid barometers use a sealed metal chamber that expands and contracts with pressure changes, moving a needle on a dial. An anemometer measures wind speed, typically using cups that spin in the wind. The faster the wind, the faster the cups spin, and this rotation is converted into a wind speed measurement. A wind vane shows wind direction, with an arrow or pointer that turns to point into the wind. By convention, wind direction is reported as the direction the wind is coming from, not going to. So a north wind is blowing from the north toward the south. A hygrometer measures humidity. Early versions use materials like hair that change length with humidity, but modern ones use electronic sensors. A rain gauge is simply a calibrated container that catches and measures rainfall. Snowfall is measured with a ruler, and snow can also be melted to determine its water equivalent. Weather stations combine all these instruments in one location. Thousands of weather stations around the world report data continuously, forming the backbone of the weather observation network. These stations follow strict standards for where and how instruments are placed to ensure measurements are accurate and comparable. Thermometers must be at a standard height above the ground, in a ventilated shelter that protects them from direct sunlight and precipitation. Wind instruments must be at a standard height with no nearby obstructions. Following these standards ensures that a temperature reading from one station can be meaningfully compared to a reading from another station hundreds or thousands of miles away. Weather satellites have revolutionized weather observation and forecasting. The first weather satellite was launched in 1960, and since then, satellites have become indispensable. There are two main types of weather satellites: geostationary and polar orbiting. Geostationary satellites orbit at an altitude of about 22,000 miles above the equator, and they orbit at the same rate that Earth rotates, so they stay fixed over one spot. This allows them to continuously watch the same area, providing images every few minutes. These satellites can track the development and movement of clouds and storms in real time. Polar orbiting satellites orbit much lower, about 500 miles up, and they pass over the north and south poles as Earth rotates beneath them. Over the course of a day, they scan the entire planet. Polar orbiting satellites can't watch one spot continuously, but they can provide much higher resolution images and can measure more detailed information about temperature, humidity, and atmospheric composition. Satellites measure weather in several ways. Visible imagery is like a photograph from space, showing clouds, land, and ocean. It's only available during daytime when the sun is shining. Infrared imagery detects heat radiation emitted by the Earth and clouds. Warmer objects emit more radiation, and colder objects emit less. Infrared imagery works day and night and can show cloud-top temperatures, which helps identify tall, cold thunderstorm clouds. Water vapor imagery shows moisture in the upper atmosphere, revealing patterns of rising and sinking air. Radar on some satellites can measure rainfall rates and storm structure. Satellites also carry instruments that measure sea surface temperature, snow and ice cover, lightning, atmospheric gases, and many other variables. The data from satellites is transmitted to ground stations and fed into weather models within minutes, ensuring that forecasters have the most current information. Radar is another crucial tool for weather observation. especially for tracking precipitation and severe storms. Weather radar works by sending out pulses of radio waves. When these waves encounter precipitation, raindrops, snowflakes, hailstones, they're scattered, and some of the energy bounces back to the radar. By measuring how long it takes for the signal to return and how strong it is, the radar can determine how far away the precipitation is and how intense it is. Heavy rain or large hail returns a stronger signal than light rain or snow. Modern Doppler radar can also measure the motion of precipitation toward or away from the radar by detecting the frequency shift in the return signal, similar to how the pitch of a siren changes as an ambulance passes you. This Doppler capability allows radar to detect rotation in thunderstorms, which is a warning sign for possible tornadoes. When radar detects strong rotation, forecasters can issue tornado warnings for specific areas. Radar has limitations. It can only see precipitation, not clouds. So if there are clouds but no precipitation, radar won't detect them. Radar beams travel in straight lines and spread out as they get farther from the radar, so they rise higher above the ground with distance. This means that far from the radar, the beam might miss precipitation that's occurring close to the ground. Mountains can also block radar beams, creating blind spots. Despite these limitations, radar is invaluable for nowcasting, forecasting what will happen in the next few hours. Meteorologists watch radar to see where storms are, how they're moving, and how they're changing, and they use this information to issue warnings and advisories. Let's think about some of the most memorable and impactful weather events in history. The Dust Bowl of the 1930s was a period of severe drought and dust storms in the American Great Plains. Years of intensive farming without proper soil conservation, combined with a prolonged drought, left the topsoil exposed and vulnerable to wind. Massive dust storms, called black blizzards, swept across the plains, blocking out the sun and burying homes and farms under drifts of dust. The dust was carried thousands of miles, reaching the East Coast and even ships in the Atlantic. The Dust Bowl forced hundreds of thousands of people to abandon their farms and migrate west, a mass exodus documented in literature and photographs. It was an ecological and humanitarian disaster that led to major changes in agricultural practices and the creation of soil conservation programs. The Great Hurricane of 1780 is considered the deadliest Atlantic hurricane on record, killing an estimated 20,000 to 22,000 people in the Caribbean. The hurricane struck multiple islands, including Barbados, Martinique, and others, with devastating effect. Ships were sunk, entire towns were destroyed, and the death toll was catastrophic. This was long before weather forecasting existed, so people had no warning. The hurricane hit during the American Revolutionary War, and it destroyed both British and French naval fleets in the Caribbean, affecting the course of the war. The Galveston hurricane of 1900 was the deadliest natural disaster in United States history, killing between 6,000 and 12,000 people. Galveston, Texas, was a prosperous port city, built on a low-barrier island in the Gulf of Mexico. The hurricane brought a massive storm surge that completely inundated the island, with water depths reaching 15 feet. Buildings were smashed, and thousands of people drowned. There was no warning because the hurricane had not been expected to strengthen as much as it did, and communication from the island was cut off as the storm hit. After the disaster, Galveston built a massive seawall and raised the elevation of the entire city to protect against future storms, an engineering feat that took years. The tri-state tornado of March 1925 is the deadliest single tornado in United States history, killing 695 people. The tornado traveled across Missouri, Illinois, and Indiana, staying on the ground for over 3 hours and covering 219 miles. Its path width was up to 1 mile in places. The tornado destroyed entire towns, and because it occurred before the era of tornado warnings and before people understood what to do during a tornado, many people were caught completely by surprise. Some didn't even realize what was happening until it was too late. The Great Smog of London in December 1952 was a severe air pollution event that killed thousands. a thick layer of fog combined with coal smoke from heating and industry to create a toxic smog that blanketed the city for 5 days. Visibility was reduced to just a few feet. People couldn't see their own feet. The smog was so thick that it penetrated indoors. Thousands of people died from respiratory problems, particularly the elderly and those with pre-existing conditions. The disaster led to the Clean Air Act and major changes in how cities manage air quality. Hurricane Katrina in 2005 was one of the most destructive and costliest natural disasters in United States history. The hurricane made landfall on the Gulf Coast as a Category 3 storm, but its storm surge, reaching up to 28 feet in places, overwhelmed levees protecting New Orleans, flooding 80% of the city. Over 1,800 people died, and damages exceeded $125 billion. The disaster exposed failures in emergency preparedness and response, and recovery took years. Katrina changed how the United States thinks about hurricane preparedness and coastal vulnerability. The European heat wave of 2003 killed tens of thousands of people across Europe. Temperatures soared to record levels and remained high for weeks. In France alone, nearly 15,000 people died, mostly elderly people living in homes without air conditioning. The heat wave stressed infrastructure, dried out vegetation and led to wildfires, caused crop failures and melted roads and train tracks. It was a wake-up call about the vulnerability of populations to extreme heat, particularly as heat waves are projected to become more common with climate change. Typhoon Haiyan in 2013 was one of the strongest tropical cyclones ever recorded at landfall, hitting the Philippines with sustained winds of 195 miles per hour. The storm surge reached 20 feet, devastating coastal communities. Over 6,000 people were killed, and millions were displaced. Entire towns were leveled. The storm highlighted the particular vulnerability of developing nations to extreme weather events and the challenges of disaster response in remote areas. These events remind us of the awesome power of weather and the importance of preparedness, accurate forecasting, and resilient infrastructure. They also show how far we've come. The death toll from similar events has decreased dramatically in countries with good forecasting, warning systems, and emergency management, though the economic costs have increased as more people and property are in harm's way. Weather interacts with ecosystems in profound ways. Plants and animals have adapted to the climate and weather patterns of their environments over millions of years. Deciduous trees shed their leaves and fall to survive winter cold. They'd waste energy trying to keep leaves alive when it's too cold for photosynthesis and when water in the soil might be frozen and unavailable. By dropping leaves, they enter dormancy and wait for spring. Evergreen trees, like pines and spruces, have needle-like leaves with a waxy coating that reduces water loss, allowing them to keep their leaves year-round even in cold climates. Cacti and other desert plants have evolved to store water and minimize water loss, with thick, waxy skins and small or no leaves. Some desert plants remain dormant for years and then spring to life after rare rainfalls, growing, flowering, and producing seeds in a matter of weeks before the desert dries out again. Animals also adapt to weather. Some migrate to avoid harsh conditions. Birds fly thousands of miles to spend winter in warmer climates where food is available. Monarch butterflies migrate from North America to Mexico to escape winter cold. Some animals hibernate, entering a state of dormancy where their metabolism slows dramatically, allowing them to survive winter without eating. Bears, ground squirrels, and bats are examples. Other animals change their behavior with the seasons. Deer grow thick winter coats and then shed them in spring. Arctic animals like foxes and hares change color, growing white fur in winter for camouflage in snow and brown fur in summer. Weather affects when plants flower and when animals breed. Many species time these events to coincide with favorable weather and food availability. If spring arrives early, plants may flower early, and if animals don't adjust their behavior accordingly, there can be a mismatch. For example, if birds migrate based on day length, which doesn't change, But the insects they eat emerge based on temperature, which is changing. The birds might arrive too late to find enough food for their chicks. These phenological shifts are one of the ways climate change is affecting ecosystems. Extreme weather events can dramatically alter ecosystems. Hurricanes can destroy forests, reshape coastlines, and create new habitat. Droughts can kill vegetation and force animals to migrate or die. Floods can wash away soil and alter river channels. Forest fires, often ignited by lightning, can clear old growth and allow new plants to colonize. Some ecosystems actually depend on periodic fires to maintain their structure. For example, longleaf pine forests in the southeastern United States need fire to clear out underbrush and allow pine seedlings to establish. Fire also opens pine cones, releasing seeds. Without fire, these forests change and lose their characteristic species. Weather also affects the spread of diseases. Many diseases are carried by insects like mosquitoes, and these insects thrive in warm, wet conditions. A wet spring can lead to population explosions of mosquitoes, increasing the risk of diseases like West Nile virus or malaria. Cold winters can kill insect populations and reduce disease transmission. Fungi and bacteria that cause plant diseases also depend on weather. Wet conditions favor the spread of many fungal diseases, while dry conditions limit them. Farmers pay close attention to weather for this reason, timing the application of fungicides and other treatments based on conditions that favor disease. The atmosphere is not uniform. It's divided into layers based on temperature. The troposphere is the lowest layer, where we live and where all weather occurs. It extends from the surface up to about 6 to 10 miles high, depending on latitude and season. Temperature decreases with height in the troposphere, which is why mountaintops are cold. At the top of the troposphere is the tropopause, a boundary where temperature stops decreasing. Above the tropopause is the stratosphere, extending up to about 30 miles. In the stratosphere, temperature actually increases with height, because this layer contains the ozone layer, which absorbs ultraviolet radiation from the sun. This absorption heats the stratosphere. The ozone layer is crucial for life on Earth because it blocks most of the harmful UV radiation that would otherwise reach the surface, causing skin cancer and cataracts and damaging plants and ecosystems. Above the stratosphere is the mesosphere, extending to about 50 miles up. Temperature decreases again with height in the mesosphere, and this is the coldest part of the atmosphere. Meteors burn up in the mesosphere as they fall from space. Above the mesosphere is the thermosphere, where temperature increases again because of absorption of solar radiation. The thermosphere is incredibly thin, with very few air molecules, but those molecules have very high kinetic energy, which is what temperature measures. This is where the auroras occur and where the International Space Station orbits. Above the thermosphere is the exosphere, where the atmosphere gradually fades into the vacuum of space. There's no sharp boundary where the atmosphere ends. It just gets thinner and thinner until it's indistinguishable from space. Weather only occurs in the troposphere because that's where moisture is abundant. The stratosphere and above are extremely dry. Water vapor can't reach those heights in significant amounts because it condenses out as air rises and cools in the troposphere. The tallest thunderstorm clouds reach the tropopause and then spread out horizontally, forming the characteristic anvil shape because they hit the stable layer of the stratosphere and can't rise further. Volcanic eruptions can inject material into the stratosphere, and because there's no weather to wash it out, volcanic ash and sulfur particles can remain in the stratosphere for months or even years, spreading around the globe and affecting climate by reflecting sunlight. Atmospheric circulation patterns create distinct climate zones around the world. We've mentioned the tropics, where warm, moist air rises, creating low pressure and abundant rainfall. The air that rises at the equator spreads toward the poles at high altitude and sinks around 30 degrees latitude, creating the subtropical high-pressure zones where many deserts are located. Between about 30 and 60 degrees latitude are the mid-latitudes, characterized by variable weather with frequent storm systems. The jet stream flows through the mid-latitudes, guiding storms. Poleward of 60 degrees are the polar regions, where cold, dry air sinks, creating high pressure. These general patterns create the planet's climate zones, but they're modified by the distribution of land and ocean, by mountain ranges, and by ocean currents. Continents heat up and cool down faster than oceans because water has a much higher heat capacity than rock and soil. This creates temperature contrasts that drive weather systems. In summer, continents become hot, creating low pressure, which draws in moist air from the oceans, creating monsoons. In winter, continents become cold, creating high pressure, which pushes dry air outward. Coastal areas have milder climates than inland areas because the ocean moderates temperature, keeping it cooler in summer and warmer in winter. This is called a maritime climate. Inland areas, far from the ocean's influence, have a continental climate with hot summers and cold winters. Mountain ranges create climate divides, with wet climates on the windward side and dry climates on the leeward side, as we've discussed. The Himalayan mountains create the dramatic climate of South Asia, with wet monsoons on the southern slopes and the dry Tibetan Plateau to the north. The Andes create a similar pattern in South America. On a smaller scale, even modest hills and valleys can create microclimates with noticeably different conditions over short distances. Microclimates are local variations in climate caused by topography, vegetation, water bodies, or urban development. A south-facing slope receives more sunlight than a north-facing slope and will be warmer and drier. A valley can be colder than surrounding hilltops at night because cold air drains downward and pools in low areas. This is called a frost hollow, and it can make the valley susceptible to frost even when nearby hilltops remain above freezing. Cities create their own microclimate, known as the urban heat island effect. Buildings, pavement, and vehicles absorb and release heat, making cities warmer than surrounding rural areas, sometimes by several degrees. Cities also affect precipitation, with the heat and roughness creating updrafts that can enhance rainfall downwind of urban areas. Bodies of water create microclimates. A lake moderates the temperature of nearby land, and in fall and early winter, when the lake is warmer than the area around the lake can be several degrees warmer than areas farther inland. In spring and early summer, when the lake is cooler than the area around the lake stays cooler. This is why fruit orchards are often located near large lakes. The cooler spring temperatures delay budding until the risk of frost has passed, and the warmer fall temperatures extend the growing season. Coastal areas experience sea breezes during the day, when land heats up faster than the ocean, and land breezes at night, when the land cools faster. These breezes can bring relief on hot days and create local clouds and showers. Forests create their own microclimate, with cooler temperatures, higher humidity, and less wind than open areas. The canopy shades the ground and reduces evaporation. Rain that falls on the canopy is intercepted and either evaporates or drips slowly to the ground, reducing runoff. Clearing a forest changes the local climate, making it hotter, drier, and more variable. Urban parks and tree-lined streets provide cooling and shade, improving comfort and reducing energy use for air conditioning. Weather phenomena can be photographed and captured in stunning ways, from time-lapse videos of clouds rolling over mountains to long-exposure shots of lightning illuminating the sky. Supercell thunderstorms, with their dramatic structure and rotating updrafts, are favorites of storm photographers. The contrast between the dark storm clouds and shafts of sunlight breaking through creates dramatic lighting. Rainbows, halos, sundogs, and other optical phenomena make beautiful subjects. The aurora borealis and aurora australis, the northern and southern lights, are among the most spectacular sights in nature, with shimmering curtains of green, red, and purple light dancing across the polar skies. The auroras are caused by charged particles from the sun colliding with gases in Earth's upper atmosphere, causing them to glow. The colors depend on which gases are involved and at what altitude the collisions occur. Oxygen produces green and red light, nitrogen produces blue and purple. Auroras are most common during periods of high solar activity, when the sun is ejecting more particles. Severe weather provides dramatic photo opportunities but also dangers. Lightning photographers use long exposures to capture multiple bolts in a single frame. Tornado photographers risk their lives to document these violent storms. Blizzards create whiteout conditions with blowing snow that obscures everything. Hurricane photographers capture the power of wind and storm surge. These images serve not just as art but as documentation of weather's impact and as tools for public education and awareness. Weather has inspired a vast scientific literature, from early observations and theories to modern physics and computer modeling. The ancient Greeks theorized about weather, with Aristotle writing Meteorologica around 350 BC, one of the first systematic treatments of weather phenomena. The word meteorology comes from this work. For centuries, weather was studied through observation and description, with little understanding of the underlying causes. The invention of instruments like the thermometer and barometer in the 17th century allowed quantitative measurement. The telegraph in the 19th century allowed weather observations from different locations to be collected and compared, revealing that weather systems move and evolve in predictable ways. This led to the first weather forecasts. The development of modern meteorology accelerated in the 20th century. With the understanding of atmospheric physics, the deployment of weather balloons and radar, and eventually satellites, the equations governing atmospheric motion were derived, and computers became powerful enough to solve them, leading to numerical weather prediction. Research continues today on many fronts, improving models, understanding severe weather, studying climate change, and exploring interactions between the atmosphere, ocean, land, and ice. Weather and climate affect human health in many ways. Heat waves cause heat exhaustion and heat stroke, particularly among the elderly, children, and those with chronic illnesses. Cities implement heat warning systems and open cooling centers during dangerous heat. Cold waves cause hypothermia and frostbite. Winter weather increases the risk of heart attacks as people shovel snow and overexert themselves in the cold. Air quality is affected by weather, with stagnant conditions trapping pollution and worsening conditions for people with asthma and other respiratory diseases. Pollen counts vary with weather, affecting people with allergies. Fungal spores and mold increase in damp conditions. Some people experience headaches or joint pain with changes in barometric pressure, though the scientific evidence for these effects is mixed. Seasonal affective disorder, as mentioned earlier, is a real condition where people experience depression during winter months, likely related to reduced sunlight affecting circadian rhythms and brain chemistry. Treatment includes light therapy, exposure to bright artificial light to simulate longer days. Weather affects mental health in other ways too. Sunny days are associated with better mood, while prolonged gray, rainy weather can be depressing. Extreme weather events, hurricanes, tornadoes, floods, cause trauma and stress that can have lasting psychological effects. Weather has economic impacts that are difficult to fully quantify. Agriculture is directly dependent on weather, with crop yields varying dramatically from year to year based on temperature and rainfall. Too much or too little of either can reduce harvests. Frost can destroy fruit crops. Hail can flatten fields of wheat. Drought can cause crops to fail entirely. Livestock are affected by weather, with heat stress reducing productivity and extreme cold requiring additional feed and shelter. Fisheries are affected by ocean temperature and currents, which influence where fish are found. Transportation is disrupted by weather, with fog, snow, ice, and high winds, causing delays and accidents. Energy production and consumption vary with weather, with demand peaking during temperature extremes. Renewable energy sources like wind and solar are obviously weather-dependent. Retail sales are affected, with warm winters reducing sales of winter clothing and cold, rainy summers reducing sales of summer items. Tourism depends heavily on weather, with ski resorts needing snow and beach destinations needing sun. The insurance industry is deeply concerned with weather because extreme events cause massive losses. Hurricanes, floods, tornadoes, hail, wildfires, and winter storms all lead to insurance claims, Insurers use sophisticated models to estimate risk and set premiums. In some high-risk areas, insurance is becoming prohibitively expensive or unavailable. Governments sometimes step in to provide insurance when private companies won't. Reinsurance, insurance for insurance companies, is a major global industry that spreads the risk of catastrophic weather events. Weather forecasting has become a business in itself, with private companies providing specialized forecasts for agriculture, energy, transportation, and other industries. These companies employ meteorologists who tailor forecasts to specific needs. A farmer might need a forecast of temperature and rainfall for the next week to decide when to plant. An airline needs forecasts of wind and storms along flight routes. A utility needs forecasts of temperature to predict electricity demand. Event planners need forecasts to decide whether to hold outdoor events. The level of detail and accuracy required varies, but all depend on the same basic science and observational data. As we drift towards sleep, thinking about weather, it's worth reflecting on how extraordinary it is that we can understand and predict these phenomena at all. For most of human history, weather was mysterious and capricious, attributed to the whims of gods or spirits. People could observe patterns and make rough predictions based on experience, but they had no way to understand why weather happened or to predict it with any real accuracy. Now we understand that weather is physics, the movement of air and water driven by energy from the sun, and constrained by the laws of thermodynamics and fluid dynamics. We can measure the atmosphere in incredible detail, simulate it in computers, and predict its behavior days in advance with remarkable accuracy. Yet weather retains an element of unpredictability and wonder. Despite all our knowledge and technology, we still can't control it. A hurricane still humbles us with its power. A tornado reminds us of nature's violence. A gentle rain or a perfect spring day fills us with appreciation for the world we live in. Weather connects us to the planet, to the sun, to the cosmos. The rain that falls today evaporated from the ocean, was carried by winds shaped by Earth's rotation, condensed in a cloud formed by rising air, and is now returning to the land, part of an endless cycle that has continued for billions of years. As you fall asleep tonight, perhaps you'll listen to the weather outside, the sound of rain on the roof, the howl of wind, or the perfect silence of a calm night. Whatever the weather, it's part of the intricate, beautiful system that makes Earth habitable and endlessly fascinating. Sleep well, and tomorrow when you wake, take a moment to look at the sky and appreciate the invisible ocean of air above you, always in motion, always changing, creating the ever-shifting spectacle we call weather.